Welcome to The Explainer. So today, we're tackling a really foundational chapter in mathematics. But look, we are absolutely not just going to sit here and memorize some dusty, complicated formula. Oh no. We're going to unlock what I honestly like to call the ultimate mathematical cheat code, the binomial theorem. Seriously, if you've ever felt completely bogged down by tedious, repetitive calculations, you are going to love how elegant this is.
Picture this. You're sitting in an exam, or maybe you're just working through a tough problem, and you're hit with this. Calculate 98 to the power of 5, without a calculator. I mean, just think about that for a second. That's 98 times 98. Taking that result and multiplying by 98 again, and again, and again. It's an absolute mountain of carrying ones and tracking place values. It would literally take forever. And let's be real, the chance of making a tiny arithmetic error along the way is basically 100%.
But you know, as the brilliant electrical engineer C.P. Steinmetz once pointed out, mathematics is a most exact science, and its conclusions are capable of absolute proofs. Math isn't about suffering through brute force multiplication. It's about finding these elegant, absolute truths that do the heavy lifting for us. We just have to find the right pattern.
So here's our roadmap for today's explainer. 1. The multiplication problem. 2. Pascal's magic triangle. 3. The binomial theorem explained. 4. Special cases and tricks. And 5. Solving impossible calculations.
Let's jump into Section 1, the multiplication problem.
Okay, let's ground ourselves with what we already know from basic algebra. You've probably had a plus b squared memorized for years, right? A squared plus 2ab plus b squared. Piece of cake. Honestly, even expanding to the power of 3 isn't too terrible. But when we start hitting higher powers, like 98 to the 5th or 101 to the 6th, that repeated multiplication becomes an incredibly frustrating hurdle. Expanding a binomial to the power of 6 requires writing out terms upon terms upon terms. We desperately need a shortcut.
Which brings us to Section 2, Pascal's magic triangle. Now this is where mathematicians started hunting for that shortcut, and a fascinating visual pattern emerges when we just focus on the coefficients, the numbers in front of the variables. At power 0, we just have 1. At power 1, the coefficients are 1 and 1. Power 2, 1, 2, 1. Power 3 gives us 1, 3, 3, 1. Do you see the hidden rule here? Every single number is just the sum of the two numbers directly above it. Add the 1 and 2 from row 2, and boom, you get the 3 for row 3. It forms this perfect endless pyramid.
We usually call this beautiful structure Pascal's triangle, named after the 17th century French mathematician Blaise Pascal. But, fun fact, it was actually discovered way earlier in ancient India by the mathematician Pingala, who called it Meru Prastara. By using this array, if you want to expand a messy binomial like 2x plus 3y to the 5th power, you don't have to multiply the whole thing out 5 times. You literally just look at the 5th row of the triangle and instantly grab your starting multipliers. It's that easy.
But yeah, there's the catch. This magic triangle has a pretty fatal flaw. What if you need to calculate something to the power of 12? Well, to build the 12th row, you absolutely have to know the 11th row. And to get that, you need the 10th. If we're dealing with really massive powers, building this giant triangle by hand completely defeats the purpose of having a shortcut in the first place.
Time for Section 3, the binomial theorem explained.
All right, it's time to level up and fix that flaw. To bypass the triangle entirely, mathematicians leveraged a concept called combinations, written as NCR. Think of combinations as a highly targeted teleportation device. Instead of agonizingly calculating all the rows up to row 12, the combinations formula lets you jump to the exact coefficient for any specific spot on any specific row, instantly. It is the magic key that unlocks this entire theorem.
Now before I show you the big, scary formula, let's just break down the underlying rules, because this really shows how simple the engine actually is. If your power is n, you are always going to have n plus 1 terms. From left to right, the power of your first variable, a, ticks down by 1 each time. Meanwhile, the power of your second variable, b, ticks up by 1. And here's the coolest part. If you add the exponents of a and b together in any single term, they will always equal n. It's like a perfectly balanced mathematical seesaw.
So let's see how this builds into the formal binomial theorem itself. And hey, don't let the notation intimidate you. This formula is literally just formalizing the exact rules we just talked about. Those NC0, NC1 parts, those are just your teleporting coefficients. The a value starts at the maximum power n and decreases, while the b value starts at 0 and increases until it hits n.
When you strip it down, it's just a really elegant set of instructions.
Moving on to Section 4, Special Cases and Tricks.
Now that we have the ultimate formula in our toolkit, let's see just how flexible it gets. When comparing a standard positive binomial with a negative one, like x minus y to the power of n, you don't even need to memorize a whole new formula. Since the negative sign is attached to the y, every single time y is raised to an odd power, that whole term becomes negative. But when it's raised to an even power, the negatives cancel out and it turns positive. So the entire sequence just beautifully alternates, plus, minus, all the way down the line.
And check this out. What if we replace that first term with the number 1? Well, 1 to any power is just 1, right? So the formula simplifies massively. 1 plus x to the power of n literally just becomes 1 plus nc1 times x plus nc2 times x squared, and so on. All those a variables completely vanish from the visual noise, which makes doing the actual calculations incredibly fast.
Finally, Section 5, Solving Impossible Calculations.
All right, let's put this cheat code to the test on that monster problem I gave you at the very beginning of this explainer. Remember 98 to the 5th power? The trick here is to rewrite 98 as something way friendlier, 100 minus 2. Now, we apply our binomial theorem for an index of 5. Instead of doing nasty multi-digit arithmetic, our terms now consist entirely of powers of 100, which, let's be honest, is just adding zeros, and powers of 2, which are tiny and super easy. And the combinations from the 5th row of Pascal's triangle give us our coefficients: 1, 5, 10, 10, 5, 1.
So you plug those in, do a little bit of basic addition and subtraction with those alternating signs we just learned about, and boom, 9,039,207,968. No way, right? You just solved a massively complex exponential problem relying mostly on addition, subtraction, and simple powers of 10. That is the sheer computational power you've just unlocked.
Here's another amazing application right from the source material. Which is larger, 1.01 to the power of 1 million or 10,000? I mean, it sounds completely impossible to know without a supercomputer. But wait, split 1.01 into 1 plus 0.01. Using our shortcut for 1 plus x, we only have to expand the first two terms. The first term is 1. The second term is 1 million multiplied by 0.01, which is exactly 10,000. So right out of the gate, just those very first two terms equal 10,001. We don't even need to calculate the rest of the positive terms to absolutely prove for a fact that it's larger than 10,000.
And honestly, that perfectly captures the core takeaway here. The binomial theorem transforms tedious, error-prone multiplication into this sleek, structural process. It proves that by understanding the underlying patterns of numbers, whether you're looking at a 17th century triangle or using the logic of combinations, we can bypass the brute force work entirely.
Now, today we focused entirely on positive integral indices, whole numbers like 5 or 6 or a million. But I want to leave you with a bit of a provocative thought. What do you think happens to this beautiful, perfectly balanced formula if the power we're raising it to is a fraction? Or what if it's a negative number? Can a pattern like this adapt to the weirdest corners of math, or does it fall apart? Keep exploring, and I'll see you next time on The Explainer.